Every single day, thousands of developers open their terminals, launch Claude Code, and watch in amazement as the AI agent writes code, runs commands, and refactors files. But behind the scenes of this revolutionary technology, a silent financial drain is occurring. If you search for a course or tutorial on how to master Claude Code, you will quickly notice a frustrating reality. The most famous guides are created by the AI companies themselves. And at the end of the day, these companies have a clear commercial incentive. They want you to spend as many tokens as possible. A few years ago, these same providers published papers advising developers to use lightweight, linear, single-prompt calls to optimize costs. Today, they tell you the exact opposite, pushing bloated, multi-agent frameworks and verbose tool loops that consume massive amounts of context and inflate your monthly billing. The most notorious example of this are autonomous agent loops. If these loops are not meticulously customized and adapted to your specific use case, they can easily get trapped in recursive error correction, run up astronomical API costs in a matter of seconds, and completely deviate from the original goal, leaving you with a half-broken codebase and a massive bill. Maximizing developer efficiency in the terminal starts at the primary interaction layer. /commands. In command line interfaces, speed and repetition are the two forces that define developer productivity. Every day, engineers type the same sequences of instructions: auditing code, formatting files, compiling builds, and drafting commit messages. If you must type a long, descriptive prompt to the AI agent every single time you want to execute a routine operation, you introduce friction, waste cognitive energy, and slow down your development loop. /commands solve this problem by serving as standardized, pre-configured shortcuts that trigger complex, multi-step agent actions. Visualize a speed dial panel on an office desk telephone. If you want to call the IT support department, the billing office, or the security desk, you do not dial their complete 10-digit phone numbers, check the area codes, and wait for intermediate routing. You simply press a single speed dial button labeled IT, billing, or security. The telephone's hardware automatically maps that single button press to the complete routing sequence in the background, establishing the connection instantly. In our terminal environment, a /command is that speed dial button. Instead of typing a long prompt like, "Please review this code for performance bottlenecks, check memory allocations, and suggest optimization strategies," you simply type /optimize. The CLI parser automatically intercepts this command and expands it into the complete, high-fidelity prompt template that you configured. The command parser operates under a structured routing pipeline. When you launch Claude Code and type a command starting with a /, the application does not treat your input as a standard chat prompt. It passes the input through an internal command parser router. The router matches the keyword against a registry of configured commands. This registry is populated from two primary locations: the user's global preferences under .claude/commands and the local project configurations under .claude/commands. If a match is found, the parser loads the corresponding Markdown template file. These Markdown template files are not simple text files. They are structured instruction sets that can contain dynamic arguments and context rules. The parser reads the file, parses the system prompts, and injects any arguments you passed in the terminal. The parsing architecture and command registration lifecycles are initialized on startup. When you launch Claude Code, the initialization engine boots up the command registry service. This service scans your project files and home directory, parsing markdown files inside the commands folders. The registration engine reads the YAML front matter and markdown body of each file, validating that the command follows correct formatting rules. If the parser encounters a syntax error or a duplicate command name, it outputs a warning in the logs and skips the file, preventing the CLI from crashing. When you type a command, the parser tokenizes the input string. It splits the string by spaces, treating the first word starting with a slash as the command key and the subsequent words as arguments. The parser checks if the command key exists in the registry. If it is registered, it loads the command execution pipeline. This execution pipeline is asynchronous. It reads the command template and dynamically evaluates any template variables, such as system context, current directory path, or Git status. For example, a /commit command template might contain variables like git diff staged. The execution pipeline intercepts this variable, executes a git diff command in the background, captures the stout output, and injects the output text directly into the prompt template. Once the template variables are resolved, the consolidated prompt is submitted to the core agent loop. The agent reads the instructions, executes the file's analysis, and returns the response. Comparing /commands to static code linters reveals key differences. A standard linter checks for syntax rules, style violations, and formatting errors using static analysis. Cannot evaluate runtime performance. The /optimize command template instructs the agent to run a semantic performance audit. The agent analyzes the code's algorithmic complexity, evaluating time and space complexity in Big O notation. It searches for common performance anti-patterns, such as nested loops that lead to quadratic time complexity, repeated database queries inside loops, and unnecessary objects instantiation that creates garbage collection overhead. Configuring custom /commands follows a simple process. To create a custom /command, you must navigate to your project directory and create the .claude/commands folder structure if it does not already exist. Inside this folder, you create a new file named after the command you want to build, using the Markdown file extension. For example, to build a /optimize command, you create a file named optimize.md. At the very top of the optimize.md file, you write the YAML front matter. The front matter specifies the name of the command and a description that the agent uses during registry search. Below the front matter, you write the instruction template. The template defines the prompt that the agent will receive. For example, you write, analyze the active code block for performance issues, time complexity, and memory leaks. Suggest specific refactoring steps to reduce latency. You can also use variables inside the template to refer to active file paths or Git changes. Resolving command priorities relies on a clear hierarchy. When you run Claude Code, it loads commands from 3 levels. First, it loads built-in system /commands. Second, it loads global user-defined commands from your home directory settings. Third, it loads local project-scoped commands from the Active Directory. If a command name collision occurs, for example, if both your global folder and your local project folder contain a file named commit.md, the command router resolves the conflict using a local overrides global rule. The local command takes highest priority, completely masking the global and system commands of the same name. This allows development teams to enforce project-specific commit rules or optimization prompts without changing their global terminal settings. Chaining /commands inside terminal pipelines enables powerful automations. Because /commands execute locally, you can pass parameters and redirect outputs. For example, you can write Claude P /optimize src /auth.js review.md. This execution runs the /optimize command on the auth.js file, captures the stout containing the optimization suggestions, and writes them to a review.md file. You can then run a subsequent command that reads the review.md file and applies the fixes. By automating this sequence, you convert manual debugging runs into rapid, repeatable shell pipelines. The Unix piping mechanism connects standard input and output streams. When you run a command in the terminal, it reads from a stream called standard input or STIN and writes to a stream called standard output or stout. By using the pipe character, you connect the stout of one command directly to the STIN of the next, creating a data processing pipeline. When you run git diff claude p /commit, the terminal redirects the stout of the git diff command to the STIN of the Claude CLI. The Claude CLI detects that STIN is not a TTY, meaning it is not a human interactive keyboard. It reads the complete STIN stream, buffers the text in memory, and appends it to the prompt. The agent reads the piped text, processes the request, and writes the output directly to stout. If you are running this inside an automated script, you can direct the stout of the Claude command to a file using the output redirect operator. For example, you write git log n5 claude p, summarize these changes, release-notes.md. The agent reads the piped git log data from STIN, processes the summary, and prints the result to stout, which the shell writes to the release-notes.md file. Terminal aesthetics and history management rely on specialized commands. When working in interactive TUI mode, personalizing your display colors and history controls improves developer comfort and record keeping. The /color command allows you to customize the color of your prompt bar. By typing /color followed by a color name or hex code, you update the border style. If you run the command without arguments, the system picks a random color, providing a unique visual separator for each session. The /compact command manages history size. If your conversation runs for too long, the history bloats, pushing the session to the dumb zone. By typing /compact, you instruct the system to summarize the past history, compressing the old turns into a brief context summary while keeping the active file edits, freeing up token space. The /export command allows you to save the session history. By executing /export followed by a file name, you write the entire markdown transcript to disk, allowing you to document the refactoring steps or share the logs with your team. The pull request template runs a git diff between your active branch and the main integration branch, parses the changes, and generates a structured, high-fidelity description containing background context, architectural impact, and a checklist of validation steps. The template parses the diff using semantic filters, separating code changes from documentation or test configuration files. It writes the description to a markdown file, saving you from writing pull request descriptions manually. Writing high-quality Git messages is automated by the commit command. Instead of writing lazy commit messages like fix bugs, the template analyzes your staged Git diff, identifies the modified classes and methods, reasons about the intent of your edits, and writes a detailed commit message following conventional commit standards. It includes a short semantic prefix, such as feat or fix, a clear summary of the primary change, and a bulleted list of secondary modifications in the body. It then automatically executes the git commit command in the background, matching your team's compliance rules without manual drafting. Repetitive terminal operations utilize the loop command. When you execute /loop followed by an instruction and a file filter, the CLI framework enters a proactive command loop. It watches the target files for modifications. When a change is saved, it automatically triggers the instruction, analyzes the edits, runs the tests, and reports the results in the terminal. For example, you can configure /loop to watch your unit tests and run them every time you modify the source files. If the tests fail, the agent analyzes the failure stack trace, proposes a bug fix, and runs the tests again. Visualizing task checklists occurs through the browser integration. When you run /ultraplan, the CLI compiles a task checklist and opens a web board. The web board renders the checklist as an interactive Kanban layout, displaying tasks as separate cards. You can drag and drop cards to adjust the execution order, edit details, and add custom scripts. Once you click Approve, the browser sends the configuration back to the CLI, which executes the tasks in sequence, displaying progress indicators in the terminal. Model configurations are adjusted dynamically. When working on different tasks, you can select which model to use and configure its default effort level. By mastering these command router integrations, you convert manual debugging runs into rapid, repeatable shell pipelines, transforming your local terminal into a highly efficient, automated software factory. Our next step is to examine how the agent maintains memory and context across these command executions. We will review how global settings relate to local overrides, trace prompt variable evaluations, and analyze how the registry handles custom command aliases and autocomplete prompts dynamically. This ensures that every developer can customize their command line interface while maintaining strict Codebase standards across their entire team. Tracing the registration lifecycle from file scan to execution ensures complete clarity. The command parser recursively scans the directories, checking for custom configurations. It builds a map of trigger keys validating metadata schemas. If a command is called, the router resolves dependencies, evaluates environment properties, compiles the output prompt, and submits it to the core agent thread. This seamless routing mechanism eliminates manual prompt writing, keeping your terminal execution fast and structured. Creating a custom code review command starts by configuring directory paths. You navigate to the repository root directory, create the .claude directory, and add a commands subdirectory inside it. Within this commands folder, you create a new file named review.md. At the top of this file, you write the YAML front matter. You define name, code review, description, analyze recent changes for architectural alignment and security, and set trigger tags. Below the YAML block, you write the markdown instructions, analyze the provided Git diff for logical consistency, naming standards, and error handling. For each issue found, state the file name, line number, issue severity, and provide a refactored code example. Once saved, you test the command by running claude p/review. The CLI router scans the commands directory, reads the file, parses the YAML block, registers the /review command, and executes the instructions template. The console outputs a clean response in your terminal, showing that the command is active and registered. Multi-stage Unix pipes redirect stout to stin. When you chain multiple tools together, standard output streams are redirected to standard inputs. For example, if you run git diff head Claude P generate commit messages, the shell maps stout of the diff command to stin of the Claude process. The CLI engine detects that standard input is not a human keyboard, checking terminal properties dynamically. It reads the piped diff bytes, stores the text in a buffer, and appends it to the commit prompt. The model processes the diff, generates the conventional commit description, and writes it directly to stout. If you redirect stout to a file using the redirect character, the shell captures the output, writing it to release notes or commit logs automatically. This piping pipeline avoids manual copy-pasting, automating your version control runs. Parameter validation checks options against schemas. When you define parameters inside your Markdown templates such as active file paths or options, the parser parses the arguments, validating them against the expected schema. If you pass invalid options, the CLI framework logs the error and prompts you for correction. By designing modular, parameterized commands, you create a customizable developer interface, letting your team trigger complex audits, run builds, and deploy updates using simple terminal shortcuts. This routing system optimizes your daily terminal workflow, converting manual tasks into fast, automated routines. Verifying command registries prevents naming conflicts. When the CLI boots up, it reads the files inside commands directories, checking if the file names contain special characters or duplicate keys. If a naming conflict occurs, the registry alerts the developer, printing a conflict resolution message to stare. It resolves the conflict by favoring local configurations over global configurations, ensuring that repository-specific templates run correctly. Once validated, the commands are registered in the active session, exposing their trigger shortcuts to the TUI parser. This dynamic registration ensures that you can edit command templates during active development without losing context, optimizing your terminal productivity and making automation simple. Argument tokenization maps target file paths dynamically. When you run a / command with arguments such as /optimize src /usercontroller.js, verbose the parser tokenizes the input. It extracts the command key, maps the target file path, and evaluates the verbose flag. It passes the argument values to the instruction template, injecting them into the prompt. The agent reads the consolidated instructions, performs the optimization audit on the usercontroller.js file, and outputs a detailed verbose analysis. This parameter injection enables you to build dynamic, reusable shortcuts that accept parameters, ensuring your development tools adapt to different file contexts and shell environments easily. Local command caching reduces startup latency. When the CLI loads your command templates, it stores the parsed YAML headers and body instructions in high-speed RAM. When you trigger a command, the router reads the template from local memory instead of executing a file system read, reducing command initialization latency to less than 2 milliseconds. This rapid execution ensures that your terminal pipeline remains responsive, preventing input lag and making automation feel instantaneous. By combining local template caching, prioritized command routing, and parameter injection, you build a state-of-the-art developer interface that streamlines your daily programming workflows, saving time and keeping your codebase stable. Integrating /commands with continuous integration pipelines automates code reviews. When integrating Claude Code with your continuous integration pipelines, you must write shell scripts that trigger /commands without manual input. For example, you write a bash script that executes the /optimize command inside your build containers, capturing the execution metrics and formatting the output logs automatically. The script maps environment variables, configuring API keys and path arguments before booting the CLI. Once the command completes, the script parses the output, checking if the agent found any critical performance vulnerabilities. If a bottleneck is detected, the script fails the build, preventing slow code from being deployed to production. This integration transforms /commands from interactive shortcuts into production-grade build gates, ensuring code quality and latency requirements are maintained across all pull requests automatically. Shell configurations load aliases and environment overrides. When executing commands, the router checks your default shell profile, loading any aliases, environment variables, or path overrides you defined in your profile configuration file. For example, you can define a shell alias that binds a custom command parameter to a key press, letting you run the /commit command with a single keyboard shortcut. This shell integration allows you to combine native terminal utilities with the agent's reasoning capabilities, creating a highly optimized, automated command line workspace. Error handling routines prevent CLI crashes during invalid lookups. If you trigger a /command that references a missing file or an invalid directory path, the command router does not crash. It catches the path resolution exception, logs a descriptive warning in the console, and prompts the agent to correct the path. If the agent cannot locate the file after 3 attempts, it terminates the tool execution and reports the failure, allowing you to debug configuration errors without losing your session history, preserving terminal stability under all execution states. Imagine hiring a freelance developer to help fix a bug in a complex legacy codebase. Instead of sitting next to them for 3 hours explaining how to run the build, where the logs are written or what styling rules they must follow, you hand them a concise onboarding handbook. The developer reads this handbook in a few minutes, immediately understands your system requirements, and starts editing code safely without interrupting your team. In our development environment, the Claude.md file is that onboarding handbook. It is a plain text markdown file stored at the root of your project directory. It does not contain code, but it defines the operational environment for the AI agent. The file contains 4 key sections: the project description, the build commands, the testing instructions, and the coding standards. When you launch Claude Code, the agent's initialization engine automatically reads this file first, caching its contents as part of the system prompt. This ensures that every tool call, file write, or test execution runs in strict compliance with your project's actual commands, preventing the agent from hallucinating invalid scripts or using wrong compilers. Organizing project memory relies on a clear hierarchy of configuration files. While the root Claude.md file establishes the primary rules for the entire repository, modern versions of Claude Code support 3 distinct tiers of memory files. The first tier is the project-level Claude.md file, which coordinates repository-wide build, test, and style commands. The second tier is the directory-level memory file, located in subfolders of a monorepo. For example, if your repository contains a Node.js backend and a React frontend, the root memory handles global rules, while the localized memory files inside the backend and frontend folders specify subpackage build and run commands. The third tier is the personal Claude.md file, which you store globally in your home settings under .claude/settings JSON. This handles global, cross-project preferences, such as your default text editor, preferred shell alias bindings, or telemetry opt-outs. Resolving rules conflicts uses a localized priority mapping. When you run Claude Code inside a subfolder, the framework's rule resolution engine performs a recursive directory scan, tracing up the folder tree from the active file path to the repository root. The resolution engine reads every memory file it encounters, merging their rules dynamically. If a conflict occurs, for example, if the root claude.md specifies cargo test as the test command, but a subdirectory memory file specifies npm test, the engine resolves the conflict using a localized priority rule. The directory-level memory file overrides the root claude.md file for all operations executed within that subfolder. This hierarchical matching allows you to manage massive monorepos with diverse tech stacks, ensuring that the back-end subagents run cargo tests while the front-end subagents run jest tests automatically. 7 distinct tiers define the agent's memory hierarchy. Listed from highest to lowest priority, these tiers are: first, the managed policy, which defines enterprise-level administrative restrictions. Second, the project memory, loaded from the root claude.md file. Third, the project rules, loaded from markdown files inside the .claude/rules subdirectory. Fourth, the user memory, loaded from your home claude.md file. Fifth, the user rules, loaded from your home rules folder. Sixth, the local memory, loaded from local temporary settings. And seventh, the auto memory, which automatically captures user preferences and interaction patterns observed during your active session. Auto memory operates silently in the background, tracking the coding style preferences you apply, the common corrections you write, your framework selections, and your communication preferences. Over time, the client learns your habits and appends them to your system prompts, ensuring that the agent's responses feel natural and customized to your development workflow. Prompt caching economics shape session performance. Modern LLM APIs charge for both processing input tokens and generating output tokens. In a standard interactive session, the conversation history grows with every prompt you send and every code block the agent writes. If the entire history had to be reevaluated from scratch by the model on every single turn, your token consumption would grow quadratically, resulting in extremely high costs and long latency pauses. To solve this, Claude Code leverages Anthropic's prompt caching. When you submit a prompt, the API checks if the prefix of the prompt matches a previously cached prefix. If it does, the API reads the cached prefix from memory instantly, processing it at a 90% discount compared to standard input tokens. Maintaining prompt caching efficiency requires a static prefix. The prefix contains the system instructions, the claude.md file, active directory listings, and the conversation history. Because the memory file is loaded at the very beginning of the prompt, keeping your claude.md static is crucial. If you modify your claude.md file frequently during a session, you invalidate the cache, forcing the API to reevaluate the entire system prompt and history at full price. To prevent this cache invalidation, you should lock down your claude.md rules before starting a development run, ensuring that the cached prefix remains warm and your execution costs stay low. Monitoring prompt cache efficiency involves analyzing local session logs. To monitor your prompt cache efficiency, you run the context stats utility in your shell. The utility reads the local session log stored in your home settings under .claude/logs. It parses the transaction records, computing the total input tokens, output tokens, and cache tokens. The tool exports a detailed summary report in the shell. This report shows your average cache hit rate. If your cache hit rate is below 70%, it indicates that the prefix of your prompts is changing too frequently. This is usually caused by dynamic data such as active file paths or logs being appended to the system instructions. By reading the report, you can identify which custom commands or subagents are inefficiently consuming tokens, allowing you to optimize your templates, lock down your Claude.md files, and maximize caching to keep your development costs predictable. Attentional limits distinguish the smart zone from the dumb zone. When you interact with the agent, the active context window represents the model's short-term memory. Large reasoning models have a maximum context capacity, typically around 200,000 tokens. However, the model's reasoning performance is not uniform across this entire window. When the active context is small, containing less than 80,000 tokens, the model operates in the smart zone. In the smart zone, the model's attention is sharp. It can track complex variables, detect subtle logic errors, and adhere to strict architectural rules perfectly. Context window expansion degrades reasoning performance. As the conversation history grows, the context expands. If the context exceeds 80,000 tokens, the model enters the dumb zone. In the dumb zone, the model's attention degrades, a phenomenon known as lost in the middle. The model struggles to locate details buried in the middle of the prompt, begins to hallucinate file paths, and frequently ignores instructions defined in your Claude.md file. Additionally, entering the dumb zone causes latency to spike, as the API spends more time processing the bloated prompt. To maintain peak reasoning performance, you must keep the session in the smart zone. If you notice the agent beginning to ignore guidelines or repeating errors, you should use the /compact command to summarize the history, or run /clear to wipe the session log and start a fresh context, keeping the agent in its smartest zone. Integrating prompt caching with personal settings optimizes CLI launches. Personal global preferences are stored in the user's home configuration directory under .claude/settings.json. This JSON file defines configurations like default model, editor, and theme. If you define a settings block inside your settings.json file, the framework reads these configurations when booting the CLI, merging them with your local Claude.md instructions. For example, you can configure your settings.json to default to Sonnet and set your default editor to VS Code, ensuring that whenever you run a file writing command, the framework launches your preferred editor automatically. Workspace organization around these memory hierarchies minimizes execution overhead. In our next section, we explore how to safeguard your workspace using version control checkpoints. To ensure complete mastery of project memory, let us trace how the agent accesses memory resources during a typical development cycle. When the session initializes, the memory engine checks the Active Directory for Claude.md, parses the content, extracting build and test targets. It maps the project overview to the system prefix, ensuring the model aligns with repository standards. During the session, the engine monitors file writes, checking if any modification affects the memory configuration. If an edit is proposed to Claude.md, the engine flags the transaction, warning you that saving changes will invalidate the active prompt cache. By establishing this proactive warning system, the framework ensures that your prompt prefix remains warm, preventing expensive cache misses and keeping your API token expenses within limits. Settings overrides integrate local rules with global configs. The global preferences JSON file is located in the user's home configuration directory under .claude/settings JSON. This configuration file contains properties, default model, editor, and theme. If you run Claude Code inside a project that contains local Claude.md guidelines, the resolution engine merges the rules. For example, your global settings.json defines the default model as Sonnet, but a local project rule specifies that the agent should run Opus for complex refactoring tasks. The resolution engine checks the project hierarchy, overriding model priorities for that folder. This priority matching ensures that global developer preferences like editor bindings remain active, while project-specific rules like linting and build commands are enforced. Prompt caching operates on a system of prefix matching. When a request is sent to the API, the gateway checks if the leading sequence of tokens matches an active cache bucket. A cache bucket is preserved in the server's high-speed memory for up to 5 minutes. If a match occurs, you receive a cache hit, and the tokens are processed at a fraction of the cost. To achieve a cache hit, the system prompt and conversation history must remain identical. If you insert dynamic values such as a timestamp or a variable file path at the very beginning of your conversation, you invalidate the cache, forcing the API to reevaluate the entire system prompt and history at full price. To prevent this, the Claude CLI structured the system prompt to place static files like claude.md and registered skills at the top of the context, while keeping dynamic values and chat logs at the bottom. This layout ensures that the prefix remains unchanged, maintaining cache warmth and minimizing billing. API pricing structures favor prompt caching. A standard input token costs $3 microdollars, while a cached input token costs only $30 nanodollars. In a development session that lasts for 50 turns, the cumulative context size can exceed 100,000 tokens. Without prompt caching, the API must reevaluate all 100,000 tokens on every turn, resulting in an aggregate consumption of 5 million tokens, costing $15. With prompt caching enabled, you pay full price for the new tokens on each turn, but the cached context is read at the discounted rate, reducing the total cost of the session to less than $2. This represents a 90% cost reduction, making interactive, long-form development sessions affordable. Attentional degradation limits model reliability in bloated sessions. Large models support massive context windows, but their reasoning capacity is not uniform. In the smart zone below 80,000 tokens, the model reads the complete context and identifies subtle bugs. In the dumb zone above 80,000 tokens, the model struggles with recall, leading to hallucinated file names and ignored rules. By using /compact and /clear, you prune the conversation history, keeping the active session in the smart zone, maintaining peak reasoning performance, and saving tokens. Context statistics profiling identifies caching inefficiencies. The utility scans the logs directory, compiling token transactions. It extracts input tokens, output tokens, and cache hit metrics, exporting them as a summary. By analyzing this report, you identify which subagent calls or commands are causing cache misses. If you see a low cache hit rate on a specific path, you adjust the claude.md file, locking down rules, ensuring that subsequent runs achieve maximum cache warmth. keeping your development costs low. The rule parser filters file exclusions and wildcards. Within the coding guidelines section, you can specify files or directories that the agent must ignore during its scanning and search operations. For example, you specify that all build outputs, lock files, and credentials files should be bypassed. The rule parser reads these patterns, converting them into regular expressions in the background. When the agent calls file search or grep tools, the CLI framework automatically filters the results, stripping ignored paths from the output. This filters the data sent to the model, preventing context bloat and securing sensitive project files from accidental reads. Custom rule subdirectories organize modular guidelines. When you have modular guidelines such as style rules for CSS styling, SQL querying safety rules, or React component standards, you should not write them all inside a single Claude.md file. This would make the file too large, reducing prompt caching efficiency. Instead, you create separate markdown files inside the .claude/rules directory. The rules engine reads these files, matching their rules to the active workspace context, ensuring that CSS rules are only loaded when editing style files, and React rules are only loaded when modifying component files. This localized rule loading optimizes your active context size, preserving space in the smart zone and keeping execution costs low. Decentralized memory rules structure large monorepos. When managing a repository that contains dozens of independent packages, a single root Claude.md file is insufficient. To prevent guidelines from getting mixed up, you establish a decentralized memory structure, placing individual Claude.md files inside each subpackage directory. The resolution engine scans the monorepo structure recursively, building a parent-child rule hierarchy. When the agent edits a file inside the gateway package, it reads the local gateway memory rules, ensuring it uses the correct routing libraries and test frameworks without loading styling rules from the client package. This directory isolation maintains cache warmth across different packages, preventing changes in one module from invalidating the prompt caches of other subprojects. Saving API tokens. Automated rule verification ensures formatting compliance. When multiple developers write code in the same repository, they must follow the registered naming conventions and architectural limits. You can write a linter script that runs during your pre-commit hooks, parsing the local rules and checking if the modified files comply with the Claude.md standards. If the linter detects a guideline violation such as a developer creating a database table without using migrations, it blocks the commit, prompting the developer to align their modifications with the project memory, maintaining system consistency automatically. Auto memory snapshots map developer habits locally. To prevent personal preference logs from bloating your project repository, auto memory writes preferences to a local configuration file stored inside your home directory under .claude/local/memory.json. The file uses a structured JSON schema, listing learned aliases, coding styles, and common corrections. The registry engine reads this file during startup, merging your personal preferences with the active system prompt. If you want to share your personal preferences with your team, you can copy these JSON rules directly into your project's Claude.md standards block, converting individual habits into shared development guidelines. How do we safeguard our active edits when an automated agent modifies multiple files in parallel? In video games, we rely on checkpoint systems, saving progress before entering a difficult dungeon so we can rewind if we fail. In our terminal workspace, Git checkpoints serve as that save game. When you ask Claude Code to execute a complex coding task such as refactoring a core API controller or updating a database interface, the agent will modify multiple files across your workspace. If the changes break the build, introduce compilation errors, or fail the unit tests, reverting those modifications manually can be tedious, especially if you have to search through your Git history to identify exactly which lines were added or deleted. Git checkpoints solve this problem by serving as automated, local save points that record the exact state of your workspace before the agent begins editing, allowing you to restore your repository to a stable state instantly if anything goes wrong. The checkpoint system integrates directly with Git branches. When you launch Claude Code inside a Git repository, the framework initializes a session tracking system. Before the agent executes its first file writing tool or runs any modifying command, it runs an automated Git status check. It identifies all modified files, staged changes, and untracked files in your workspace. The framework then automatically creates a temporary checkpoint branch in the background. The branch name contains the session ID and a timestamp. The system stages all changes and commits them to this temporary branch, creating a clean save point. This background checkpoint creation is invisible. It does not clutter your active Git commit history or push branches to your remote repository. Reverting workspace changes utilizes the /undo and /rewind commands. The /undo command reverts the single most recent file write or tool execution, restoring the affected files to their exact state before that specific action occurred. The /rewind command is a more powerful rollback utility. When you run /rewind followed by a turn index or timestamp, the framework identifies the corresponding save point on the temporary checkpoint branch. It runs a git reset hard command to discard all modifications made after that save point, checking out the exact file states from the checkpoint. This rollback is safe, as the framework preserves your unstaged work in a temporary stash before executing the reset, allowing you to undo the rewind if you change your mind. Local backup directories protect untracked files from deletion. A common danger in automated coding is the accidental deletion of untracked files such as local environment configurations, draft documentation, or temporary test scripts which are not tracked by Git and therefore cannot be restored using standard Git checkout commands. To protect your untracked files from accidental loss, Claude Code maintains a local backup cache in your home settings under .claude/backups. Before writing to or deleting any file, whether tracked or untracked, the framework copies the active file content to this backup directory. The backup file is indexed by its absolute path and the session ID. If the agent deletes an untracked configuration file by mistake during a refactoring run, the framework scans the backup cache, retrieves the cached file content, and restores it to its original path, protecting your workspace from data loss. Eviction policies manage the backup cache footprint. Over weeks of active development, the backup directory under .claude/backups can accumulate thousands of files, consuming gigabytes of disk space. To prevent the cache from bloating your file system, the framework includes an automated cache eviction policy. When the total size of the backup folder exceeds a pre-configured threshold, such as 1 gigabyte, the system automatically deletes the oldest backup files based on their access timestamps. You can also trigger this cleanup manually by running a clean command, which wipes the backup directory and frees up disk space instantly. Customizing checkpoint branch prefixes avoids team collisions. When working in shared repositories, You should ensure that your temporary checkpoint branches do not conflict with your team's branch naming conventions. To prevent naming collisions, you can customize the checkpoint prefix in your settings.json file. For example, you can set the prefix to contain your developer username, ensuring that all local checkpoints are grouped under your personal namespace. Additionally, you should configure your git ignore rules to exclude the .claude directory from version control, preventing temporary session logs or backup caches from being committed to the shared repository. Automated commit logs document session history. By leveraging these checkpoints and backup directories, you establish a reliable safety net for all automated editing tasks. This safety net allows you to run complex, multi-file refactoring runs with complete peace of mind, knowing that you can revert your entire workspace to a clean state instantly if the agent's edits fail to compile or break your builds. In our next section, we explore how to customize your terminal user interface and CLI options to optimize your interactive sessions. We will trace the detailed terminal outputs produced during a rewind execution, look at how the backup cache hashes file paths to prevent name conflicts, and evaluate the performance implications of checkpoint operations during heavy local builds. This will give you the baseline security mindset required to run complex automated scripts in production environments. The framework writes temporary commits during active sessions. When a file write is completed, the checkpoint engine appends the delta to the session branch. If a rollback is requested, it checks out the revision index, restoring active files without manual merges. This automated backup routing ensures that your workspace remains clean, protected, and fully recoverable under all conditions. File path hashing prevents name collisions inside backups. The backup directory is located in the user's home configuration directory under .claude/backups. Within this folder, the system creates a flat file structure. When you ask the agent to edit a file, the backup engine hashes the file's absolute path to create a unique file name, preventing name collisions if multiple projects contain files with the same name. For example, if you edit a file named database.js in two different repositories, the backup engine hashes their absolute paths, creating two distinct backup files. The engine writes a metadata JSON file next to each backup, recording the original file path, the session ID, the user's Git branch, and a timestamp. If you run /undo, the engine reads the metadata, matches the active path, retrieves the cached file, and overwrites the active file, restoring your workspace instantly. Weekly cleanup scripts optimize Git repository performance. Over weeks of development, the local Git repository database can accumulate hundreds of temporary session branches, increasing the repository size and slowing down Git operations. To maintain Git performance, you can write a shell script that runs weekly, identifying and deleting session branches that are older than 14 days. The script runs git branch D on the expired namespaces, ensuring your local Git registry remains clean and fast. Conflict resolution gates prevent overwrites during rollbacks. In some situations, you might make manual modifications to a file while the agent is running in the background. If you attempt to rewind the session to an older checkpoint, the engine detects that the local file contents differ from both the checkpoint state and the baseline stash. To prevent overwriting your manual changes, the engine pauses the rollback, printing a merge conflict warning. Prompts you to either commit your local changes first, discard them, or run a three-way merge. By enforcing this safety gate, the framework protects your manual work, ensuring that automated rollbacks never corrupt your active edits. Remote session archiving secures enterprise development. In enterprise environments, teams often run daily backups of developer sessions to secure work and analyze productivity. You can write a shell script that runs after your Claude sessions, compressing the local checkpoint branch into a zip file and uploading it to a centralized storage server. This remote archiving ensures that if a developer's machine fails, their session history, temporary branches, and local backups can be recovered instantly, keeping your development operations stable and resilient against data loss. Stash popping verification resolves line conflicts. If you have unstaged edits in your workspace and trigger a rewind, the checkpoint engine automatically stashes your changes to keep the rollback clean. However, if the stashed edits modify the same lines of code as the checked out checkpoint files, popped stash conflicts occur. To resolve this, the engine pauses the popping process, writing Git conflict markers into the affected files. It prompts the developer to run a merge utility or select which edits to keep. By implementing this conflict gating, the system ensures that stashed edits are never overwritten silently, protecting your manual work during heavy debugging runs. Temporary branch management runs cleanups periodically. Secret scanning sweeps secure local Git history. In large organizations, security teams must verify that developers do not commit credentials, passwords, or proprietary keys to local Git repositories. You can configure a security scanner to audit the temporary checkpoint branches automatically. When a session ends, the scanner reads the checkpoint commits, running pattern matching checks on all modified code lines. If a secret exposure is detected, the scanner logs the violation, alerts the security officer, and wipes the credentials from the local Git history, securing your organization's assets. Consider configuring the instrument panel on a custom racing vehicle. Professional drivers do not accept default dashboard layouts, rigid steering wheels, or fixed mirrors. They adjust the seat height, calibrate the pedal pressure, configure the heads-up display to show only critical telemetry, and map custom shortcut buttons to their steering wheel controls. This personalization ensures that during high-speed races, they can monitor vital metrics and execute split-second maneuvers without taking their eyes off the track or wasting physical effort. Customizing your terminal user interface serves the same purpose. When you run Claude Code inside your shell, the default settings might not match your terminal emulator's capabilities, keyboard layout, or preferred visual aesthetic. The CLI framework provides a suite of interactive configuration tools including TUI toggles, scroll speed controllers, custom key bindings, and color theme managers that allow you to tune the terminal environment to your exact specifications, optimizing readability and reducing keyboard friction during long development sessions. REPL modes bypass full-screen terminal rendering issues. When you launch the CLI, it initializes a full-screen interactive TUI shell. The TUI divides your screen into three primary panes: the active conversation history pane, the live preview file pane, and the prompt input bar. However, in some terminal emulators or remote SSH connections, rendering this complex full-screen interface can introduce significant latency, screen flickering, or line truncation bugs. To resolve these rendering issues, you use the /2a command. The /2a command toggles the interface mode, switching the terminal from the full-screen TUI layout to a standard, stream-oriented REPL shell. In stream mode, input is read from STIN and output is written to stout sequentially. This stream mode bypasses terminal rendering buffers entirely, providing a lightweight, low-latency interface that works perfectly across any SSH connection or minimal terminal emulator. Scroll sensitivity configurations adapt TUI preview panels. When reviewing long file diffs in the TUI Live Preview pane, you use your mouse wheel or trackpad to scroll. Depending on your operating system's mouse settings, the scrolling speed can be too slow or too fast. The /scroll speed command allows you to tune this sensitivity. By executing /scroll speed followed by a positive or negative number, you adjust how many lines the preview pane scrolls per tick. This setting is saved to your homesettings.json file, ensuring a smooth file reviewing experience across all subsequent development runs. Keyboard shortcut mappings customize cursor controls. By default, the input bar uses standard Emacs key bindings for text editing, such as Ctrl-A to move the cursor to the beginning of the line and Ctrl-E to move it to the end. If you are a Vim user, or if your keyboard layout requires custom key mappings for terminal control, you can customize these key bindings. The /key bindings command opens a configuration interface where you can map standard terminal keys like page up, page down, or delete to specific editor actions, adapting the terminal interface to your personal typing standards. Reasoning depth settings manage token allocation budgets. When working on different tasks, you can select which model to use and configure its reasoning depth. The /effort command allows you to adjust this reasoning depth using an interactive slider in the terminal. You can select effort levels, low, medium, or high. For simple file formatting or search tasks, you can set the effort level to low, reducing the model's thinking tokens and saving on API costs. For complex debugging or architectural planning tasks, you can set the effort level to high, instructing the model to consume more thinking tokens and reason deeply to prevent logic errors. Visual Theme Picker commands update ANSI color schemes. To customize the interface's color scheme, you use the /theme command. The /theme command opens a terminal theme picker, displaying a list of built-in themes like dark, light, solarized, and high contrast. When you select a theme, the CLI framework automatically updates the ANSI color variables used to render the prompt bar, error logs, and diff borders. You can also create custom themes by writing JSON files inside the user's home configuration directory under .claude/themes. Within the JSON file, you map UI components like prompt bars, error messages, and diff highlights to standard ANSI or hex color values. Interface optimization maximizes terminal comfort and readability. By customizing these interface modes, key bindings, and reasoning settings, you optimize your terminal environment for speed and comfort, ensuring that you can review code, edit files, and monitor execution metrics efficiently. In our next section, we explore how to extend the agent's capabilities with permanent, specialized expertise using agent skills. We will analyze how settings.json saves your customized scroll sensitivities and key mapping indices, evaluate terminal capabilities check lifecycles, and explore how to troubleshoot rendering errors across legacy shell layouts. The Layout Manager renders visual updates dynamically. When a render tick occurs, the manager computes pane boundaries, checks theme variable definitions, updates borders using ANSI codes, and draws the input bar. If a resize occurs, it redraws the grid instantly, ensuring that lines fit your screen width without wrapping errors, maintaining a clean visual state across your terminal sessions. Raw terminal mode capturing intercepts interactive key presses. Full-screen terminal user interfaces operate by manipulating the terminal's raw mode, disabling standard line buffering and echoing. This allows the application to capture key presses instantly and redraw the screen. However, this raw mode rendering requires sending complex ANSI escape sequences to the terminal to clear the screen, position the cursor, and draw colors. If your terminal emulator does not support these ANSI sequences, or if you run the CLI inside a remote SSH session with a slow network connection, the full-screen redraws can fail, causing visual glitches, line wraps, and input lag. By running /2a, you switch the CLI to REPL mode. In REPL mode, the application uses standard line buffering, printing responses as simple scrolling text. This stream mode works on any terminal, ensuring compatibility and low latency. Scroll speed adjustments update settings profiles dynamically. Within your home settings.json file, the TUI configuration block contains a property, scroll speed. The default value is set to 3, meaning each tick of the mouse will scrolls the live preview pane by 3 lines. If you run /scroll speed and pass a new value, such as 5, the framework updates this settings property. When you scroll in the preview pane, the TUI event loop reads this setting, shifting the viewport offset by the configured number of lines. This updates the screen buffer, rendering the new lines instantly and providing a smooth scrolling experience. Keyboard map arrays bind command triggers in settings. Within settings.json, you can define a key bindings map. This map matches terminal key codes to editor actions. For example, if you want to map the page up key to scroll the preview pane, you write a key bindings entry, mapping the page up ANSI escape sequence to the preview scroll up action. When you press the page up key, the input reader captures the escape sequence, matches it against your key bindings map, and triggers the preview scroll action, allowing you to navigate long files without using the mouse. ANSI color properties map UI elements to custom themes. The theme files are JSON documents stored in your home directory under .claude/themes. Within a theme file, you map UI elements like prompt borders, alert boxes, and line numbers to specific terminal colors. You can use standard ANSI color names, such as red or blue, or 256 color palette indexes. When you run /theme, the theme manager reads these files, compiles the color variables, and applies them to the TUI rendering loop. This updates the display colors instantly, letting you customize the interface to match your personal terminal styles. Config validation logs syntax warnings during initialization. The CLI boots up, reads settings.json, and initializes the raw mode terminal interface. It checks your terminal capabilities, loads the color variables, and maps the custom key bindings. If settings.json contains syntax errors, the initialization engine prints a warning, loads default configurations, and launches the TUI, ensuring that you can always start a session even if your settings are temporarily broken. Dynamic window scaling wraps text blocks cleanly during splits. In modern desktop environments, developers frequently resize their terminal windows or split their screens to view code side by side. When a resize occurs, the terminal emulates a window change signal to the active process. The TUI Layout Manager intercepts this signal, pausing input processing, reading the new window dimensions, and recalculating the grids for the conversation and preview panes. It redraws the screen borders and wraps long text blocks to fit the updated width, preventing line truncation and visual distortion. This dynamic scaling ensures that your visual workspace remains clear and readable, regardless of how you arrange your development windows. Shell configuration profiles export global environment overrides. If you want to customize Claude Code across all terminal sessions, you can export environment variables such as Claude_theme, Claude_editor, or Claude_default throttle inside your shell's RC file. When the CLI executes, it checks these environment variables, overriding the settings defined in your global settings.json file. For example, by exporting Claude_theme equals solarized, you instruct the system to load the solarized theme automatically on boot, allowing you to manage your developer preferences using standard shell configurations, ensuring a unified terminal aesthetic. Properties mapping tunes session options inside settings.json. Within your home settings.json, the root JSON object supports configuration keys, max history limit, default reasoning effort, telemetry enabled, and shell path overrides. The max history limit property accepts an integer value, defining the maximum number of conversation turns preserved in your session history before the CLI triggers automated history summaries. The default reasoning effort property accepts string values, low, medium, or high, establishing the baseline effort level for Sonnet models during active sessions. The telemetry-enabled property accepts Boolean values, allowing you to disable analytical telemetry reporting completely, securing your session metadata. The shell path overrides property accepts string paths, mapping custom shell executables for automated tools. By configuring these properties, you customize the framework's runtime environment, optimizing performance and resource allocation. Startup profiling audits config parsing overhead. When you launch the CLI, the initialization engine reads your home settings.json file, parses the JSON keys, scans the color theme files, and maps key bindings. If you have configured dozens of custom plugins, large themes, and extensive key mappings, the initialization engine can spend hundreds of milliseconds parsing these configurations. To maintain a fast startup speed, you should keep your global settings.json file structured and lightweight, archiving old themes and disabling unused plugins to ensure the CLI boots in less than 50 milliseconds, providing a rapid, interactive experience. Fallback borders maintain readability on legacy shells. If you run the TUI inside a legacy terminal or a minimalist shell, the layout borders, line wrapping, and scroll indicators can render incorrectly, causing screen distortion and visual glitches. This is usually caused by missing support for Unicode characters or ANSI escape sequences. To resolve these visual glitches, you can configure your settings.json to disable custom borders and scroll bars. Fallback to plain ASCII representation. This fallback configuration ensures that the interface remains readable and functional, regardless of the rendering limits of your desktop terminal emulator. Picture a retro video game console that accepts physical cartridges. The console contains a default operating system, but to play a specialized flight simulator, you slide a cartridge into the slot, instantly loading new rules and assets. Agent skills represent those specialized cartridges, while / commands serve as simple shortcuts that you must invoke manually by typing in the terminal. Skills represent a more advanced, auto-discovered extension tier. A skill is a packaged bundle of instructions, helper scripts, configuration schemas, and reference documentation that is loaded dynamically by the agent. By creating custom skills, you provide the agent with specialized, repository-specific expertise, allowing it to act as a code reviewer, an API documenter, or a database specialist without cluttering your global prompt settings. Directory scan services locate skill manifests recursively. To build a skill, you create a dedicated folder either globally in your home settings under .claude/skills or locally in your project under .agents/skills. When you launch Claude Code, it automatically scans these directories. It indexes the available skills, reads their configurations, and registers them in the active session. Each skill folder must contain a primary instruction file named skill.md. This file is written in Markdown but starts with a YAML front matter metadata block at the top, enclosed between triple dashes. YAML schemas validate front matter parameters. The YAML front matter defines the metadata and operational constraints of the skill. It contains 3 required fields: the name of the skill, a detailed description, and a list of trigger rules. For example, if you are building a code review skill, you write name equals code review, description equals review code changes for style and quality, and configure it to trigger when a user runs a/review command. Below the front matter, the body of the skill.md file contains the detailed system instructions that shape the agent's behavior. The skill directory can also contain subfolders to organize resources, such as scripts, templates, and references. Context forks isolate subagent context windows. When the agent triggers a skill, it must execute the instructions without diluting the primary conversation history. If the skill requires the agent to analyze hundreds of files, the conversation history can bloat, pushing the session to the dumb zone and saturating your context window. By setting context equals fork inside the front matter, you instruct the system to run the skill in complete isolation. When the skill is triggered, the system automatically spawns a temporary child session. The child session receives a copy of the active file context and the skill instructions, but does not load the parent conversation history. The subagent executes the skill tasks inside this isolated bubble, writes the outputs to the files, and returns only the final summary to the parent session. This isolated execution prevents context pollution, keeping your primary session clean and fast. Allowed tools properties enforce security restrictions. When writing custom skills, you often want to restrict what tools the agent can execute. For example, if you write a skill to generate API documentation from source code, the agent should only read files and write the documentation. It should not run build commands, modify package dependencies, or delete files. To enforce this security boundary, you configure the allowed tools key inside the YAML front matter. The allowed tools key lists the specific tools the agent can run while the skill is active. This configuration restricts the agent to read-only tools while the skill is active. If the agent tries to run a write file or edit file tool, the framework blocks the tool execution and returns a security error to the model, protecting your code base from unauthorized modifications. Argument autocomplete hints display parameters in TUI. To improve the user experience in the terminal, skills support autocomplete hints. When you configure a skill, you can define the argument hint property in the front matter. For example, you set argument hint sadface filename or argument hint sadface format. When you type the skill /command name in the prompt bar, The TUI autocomplete system reads this key and displays the hint in gray text next to the command. This visual feedback tells you exactly what arguments the command expects, reducing syntax errors. Registry scanning paths prioritize folder settings. In large projects, different subfolders can require different variations of the same skill. For example, your backend subfolder might require a code review skill that checks for SQL injection, while your frontend subfolder requires a review skill that checks for React rendering performance. To handle this, the skill resolution engine searches for.agents/skills folders recursively. The skill folder closest to your active file is loaded, overriding the root skill. This directory-scoped overriding allows you to define specialized rules for each component of your codebase while keeping your global settings unified. Dynamic registration enables modular skill integrations. By structuring your custom prompts and instructions into these auto-discovered, directory-scoped skill cartridges, you build a modular extension system, allowing you to adapt the agent's behavior to the specific requirements of each codebase component. In our next section, we explore how to monitor and validate these actions using system hooks. We will review how to configure allowed tools lists, trace the subagent creation lifecycle when context equals fork is enabled, and inspect how autocomplete inputs map commands to target files dynamically. The resolution engine scans for skills dynamically. When you launch a command, it traces up the directories, looking for skill configuration files, parses metadata keys, matching definitions to active paths. If a skill folder is found, the engine initializes the tool's restriction list, wraps the workspace context, and executes the skill instructions, providing localized rules without polluting global settings. YAML syntax checking prevents skill loading errors. When you define a skill inside your project directory under .agents/skills, the CLI Framework's registry service scans the markdown files. The registry uses a YAML parser to read the front matter block at the top of each skill.md file. It validates that the front matter contains required fields, name, description, and trigger rules. If the front matter is valid, the service reads the markdown body, compiling the instructions into the active system prompt. If the parser encounters a formatting error such as an invalid YAML key or a missing name property, it prints a validation warning to standard error, skipping the skill folder, preventing registry crashes. Child session allocation controls token consumption. When the agent triggers a skill configured with context equals fork, the framework's delegation engine spawns a child subagent process. The delegation engine copies the active file paths and the skill system prompt to the child session, but it does not copy the parent conversation history. The child subagent runs in a completely separate context window, isolating its API token usage. The subagent reads the files, executes the skill tasks, and writes its modifications back to the workspace. Once completed, the child session terminates, returning only the final execution report to the parent agent. This isolation preserves the parent session's context window, keeping it small and fast, preventing token bloat, and saving on API costs. Permission validation gates block unauthorized file modifications. Within the YAML front matter of your skill.md, the allowed tools property defines a strict security gate. The property accepts a list of tool names, such as red, grep, and glob. When the agent executes a tool while the skill is active, the framework security engine checks this allowed tools list. If the tool name exists in the list, the engine approves the call. If the agent attempts to run a write file or edit file tool that is not in the allowed tools list, the security engine blocks the execution, returning a tool permission denied error to the model. This read-only boundary protects your codebase, ensuring that untrusted or automated skills cannot modify files or execute dangerous commands. Directory search rules resolve local overrides recursively. In large projects, you can define different skills for different subfolders. The registry service resolves these local definitions by searching the directory tree recursively. It traces up the folder paths from the active file, loading the closest skill.md file it finds. This local overrides global rule allows you to define custom back-end refactoring rules inside your server directory, while keeping standard front-end styling rules inside your client folder. By organizing your skills into these isolated folders, you manage complex, multi-language monorepos easily, ensuring that the agent always runs the correct commands for each file. Custom skill configuration templates generate Jest test suites. To generate tests, you navigate to your repositories.agents/skills directory and create a new folder named Test Generator. Inside this folder, you create the main skill.md file. At the top of the file, you write the YAML front matter, defining name, unit test generator, description. Automatically generate comprehensive unit tests for modified source files, allowed tools, read, write, bash, and trigger rules. Below the YAML metadata, you write the detailed instruction prompt. Analyze the target source file, identify all exported functions, methods, and classes. Write Jest test suites that cover edge cases and error states. Execute the npm test command to verify compliance and report any failures. You save this file and copy a helper script into the same directory to automate test execution checks. Once you launch the CLI, the registry scans the folder, parses the YAML configuration, and loads the skill, allowing you to trigger automated test generation using simple shortcuts. Autocomplete parameters display gray text hints in prompt bars. When you trigger a skill using a custom / command, you can append parameter values in the terminal. The argument parser reads these inputs, validates them against your YAML parameter schemas, and binds them to specific template variables. The agent reads these variables, customizing its behavior. For example, if you run a code audit skill with the parameter severity equals high, the agent focuses exclusively on critical security vulnerabilities and performance bottlenecks, bypassing minor style warnings. This dynamic parameterization ensures that your custom skills remain flexible, allowing you to run focused audits under different development scenarios. Relative path mapping translates resource dependencies dynamically. If a custom skill relies on external templates or helper scripts stored inside the skill directory, the Path Resolution Manager maps these relative paths to absolute coordinates dynamically. When the agent references a relative path inside its system prompt, the framework translates it, ensuring the helper scripts execute correctly regardless of your active working directory. This path translation makes your custom skills fully portable, allowing you to distribute them across different repositories and systems without changing file references. Tool whitelisting limits subagent command options securely. If you assign a skill to an external developer or use a public automation script, you must protect your system from malicious or unauthorized commands. By restricting the skill's allowed tools to read, grep, and glob, you block the agent from executing write operations or shell commands. ensuring the agent can analyze your files and report findings safely without risking code corruption or exfiltrating data, providing a secure workspace boundary for all delegated runs. Caching instruction sets saves CLI startup time. When the registry service scans your projects.agents/skills directory, it parses the markdown files and compiles the instruction sets into a binary cache format. When a skill is triggered during an active session, the framework loads the compiled instructions directly from this local cache, reducing the skill initialization overhead. This caching mechanism optimizes token usage, as the compiled instructions do not need to be reparsed on every tool call, keeping your session fast and cost-effective, ensuring a smooth automation workflow. Imagine the security protocol of a secure bank vault. An employee retrieving a document must first present their credentials to a security officer. If valid, the vault door opens. Before leaving, the employee passes through a second security scanner to verify they carry only authorized files. System hooks act as this multi-layered security pipeline in our shell. A hook is an event-driven script that runs automatically at specific points in the agent's execution cycle. The CLI framework supports 3 primary hooks: pre-tool use, post-tool use, and session start. When the agent attempts to run a tool such as writing to a file or executing a shell command, the pre-tool use hook intercepts the action, running validation checks in the background. If the hook script returns a non-zero exit code, the framework blocks the tool call and returns the stare to the agent, instructing it to correct the lint issue before retrying. Environment variables expose event details inside JSON payloads. When a hook executes, the CLI framework passes details about the active event to the script through an environment variable named Claude_hook_payload. The payload is formatted as a single JSON string. It contains fields, event type, tool name, arguments, and proposed changes. To read these specific fields inside your shell script, you use the JQ parser utility. For example, you write echo $Claude_hook_payload JQ.toolName. This allows your hook scripts to inspect the proposed edits and arguments programmatically. Pre-tool use validation hooks execute linters before files write. When you write code, you want to verify that the edits do not introduce syntax errors. To automate this check, you create a pre-tool use hook script. When the agent calls the edit file tool, the framework pauses execution, writes the proposed changes to a temporary file, and runs your hook script. The hook script runs ESLint on the temporary file. If the linter detects a syntax violation, it prints the error and exits with code 1. The framework captures this exit code, blocks the write file tool execution, and sends the linter's error log back to the agent as tool output. The agent reads the error, modifies the code to fix the syntax violation, and attempts to run the tool again. This automated feedback loop prevents invalid code from ever hitting your file system. Post-tool use auditing processes test coverage reports. While pre-tool use hooks validate tool inputs, post-tool use hooks audit tool outputs. For example, after the agent runs a test command, the post-tool use hook can parse the test report, checking if any tests failed or if code coverage dropped. If the hook detects a coverage drop, it exits with code 1, blocking the task completion and instructing the agent to write more unit tests to restore coverage. Session start environment checks identify outdated node modules. The session start hook runs when you launch Claude Code, before the main conversation prompt is displayed. This hook is useful for setting up your environment, such as running a git fetch to pull the latest changes, or checking if your node dependencies are up to date. If the hook detects outdated packages, it outputs a warning in the terminal, advising you to run npm install before starting your session. Workspace directory variables assist path resolution inside hooks. Along with Claude_hook_payload, the framework sets variables like Claude_workspace_dir and Claude_hook_. These variables allow you to write reusable hook scripts that adapt to different project layouts. For example, your pre-tool use hook script can read Claude_workspace_dir to locate the project's config files, ensuring the checks run with the correct lint settings regardless of which subfolder you launched the CLI from. Recursion level guards prevent nested execution loops. When you write a hook that runs shell commands, you must be careful. If your hook script runs a command that triggers another tool call, it can cause an infinite loop, spawning hundreds of nested hook processes and crashing your terminal. To prevent this recursion, the framework sets a recursion guard variable named Claude_hook_recursion_level. When a hook script runs, it checks if this variable exists. If the recursion level exceeds a pre-configured threshold such as 5, the hook script exits immediately with code 0, breaking the loop and keeping your terminal stable. Dr. Diagnostics check local tool installations. The /hooks command prints a detailed summary of all registered hook scripts, showing their file paths, event triggers, and active status. If a hook script is behaving erratically or slowing down your terminal, you can run /hooks disable to turn it off temporarily. The /doctor command runs a system diagnostic check, auditing your node version, git path, global settings, and hook scripts to verify that they are configured correctly and do not have syntax errors, helping you troubleshoot hook issues. Validation pipelines block invalid edits automatically. By writing these automated pre-tool use, post-tool use, and session start hooks, you build a robust quality gate that monitors and validates every agent action, ensuring that all file modifications compile and comply with your team's coding rules. In our next section, we explore how to connect the agent to external databases and third-party APIs using the Model Context Protocol. We will analyze the environment payloads in depth, trace validation checks inside system hooks, and explore how to troubleshoot exit status blocks dynamically during automated CI/CD pipelines. The Hook Manager runs diagnostic scans. When a session starts, it reads trigger configs under commands. It binds events to target file filters, validating that script files exist. If a hook fails to run within the timeout window, the manager terminates the process, returns a warning log, and lets the session proceed, keeping your terminal responsive. JSON parser utilities read tool arguments inside scripts. When an event triggers a system hook, the CLI framework compiles execution details into a JSON payload. The payload is exposed to the hook script via the environment variable, Claude_hook_payload. The JSON structure contains fields, event type, tool name, arguments, and proposed changes. For example, when the agent calls the edit file tool on a file, the event type is set to pre-tool use, the tool name is set to edit_file, and the arguments object contains the target file path. The proposed changes object contains the original code and the refactored code. To read these specific fields inside your shell script, you use the JQ parser, parsing the JSON string dynamically. For example, you write echo $Claude_hook_payload jq.arguments.path. This allows your hook scripts to inspect the proposed files and edit blocks programmatically, enabling automated validations. Linter output logs assist automatic bug fixing. When Claude Code executes a hook script, it monitors the script's exit status. If the hook script runs successfully without detecting errors, it exits with status 0. The CLI framework reads this exit code, approves the event transaction, and executes the agent's tool call. If the hook script detects a validation error such as a linter error or a security violation, it prints the error log to standard error and exits with status 1. The framework captures this non-zero exit code, blocking the tool execution. It routes the standard error output back to the agent, instructing it to resolve the linter error and retry the tool call. This automated blocking ensures that compilation errors never hit your repository. Session-end hook scripts run cleanup tasks on exit. When the active Claude session terminates, the framework automatically triggers the session-end hook. This hook is useful for running cleanup operations, such as deleting temporary folders, pruning the backup cache, or exporting the session logs to a shared storage directory. The session-end hook receives details about the completed session, including total tokens consumed, session duration, and final commit hashes via the Claude_hook_payload variable. By parsing these metrics, you can generate automated summary reports, detailing the tasks accomplished and the aggregate API costs, keeping your development metrics organized. Profiling execution times optimizes interactive terminal performance. Because the pre-tool use hook executes synchronously before every file modification, running slow validation checks such as full test suites or deep security scans can introduce significant typing latency, making the terminal feel slow. To maintain a responsive editing experience, you should keep your pre-tool use checks lightweight, focusing only on syntax verification and formatting rules. You should defer heavy audits such as integration tests or code coverage checks to the post-tool use hook or your background CI/CD pipelines, ensuring your terminal remains fast and interactive. Synchronous validation profiles record hook execution overhead. When running multiple hooks in your development environment, you must monitor the overhead they add to your tool executions. If your pre-tool use hook script queries remote web services or compiles heavy TypeScript resources synchronously, the agent's file writing operations will experience delays of several seconds, disrupting your interactive development loop. To minimize this latency, you can profile your hook execution times using the /hooks command with the profile flag. The command exports a detailed audit report showing the runtime execution times of each active hook script. If a hook's runtime exceeds 100 milliseconds, you should optimize the validation scripts, caching intermediate build files, or executing remote requests asynchronously to ensure the agent's tool calls execute instantly. Sandboxed hook execution environments prevent security leaks. When running third-party validation scripts inside your pre-tool use hooks, you must protect your system from unauthorized network calls or local file system access. You can configure the hook executor engine to run your scripts inside a restricted container, blocking the hook from accessing folders outside your project directory or communicating with external IP addresses unless explicitly whitelisted in your settings. This sandboxed execution secures your local environment, protecting your workstation from malicious hook logic. Fallback handlers bypass broken hook scripts safely. If a hook script crashes due to a syntax error or a missing binary dependency during a tool execution run, the hook manager does not hang. It catches the script execution exception, logs a warning message to stare, and overrides the hook execution status, automatically approving the agent's tool call. This fallback mechanism ensures that configuration errors inside your validation scripts do not block your development runs, letting you continue editing and debugging your code while alerting you to fix the broken hook configuration in the background, keeping your development operations stable. Visualize an international delegation meeting where everyone speaks a different language. Rather than forcing every delegate to learn a dozen foreign tongues, they route all statements through a single translator fluent in Esperanto. The Model Context Protocol acts as that universal translator for terminal agents. While standard LLM APIs are designed to process text, they cannot interact with external systems such as databases, Jira backlogs, Salesforce records, or GitHub APIs directly. Every third-party service uses a different proprietary API format. Instead of building custom integrations for every service, the Model Context Protocol establishes a standard client-server interface. The Claude Code client acts as the MCP client, while external services run MCP servers. The servers expose data resources, tools, and prompts using a unified JSON RPC schema, allowing the agent to read databases, fetch issues, and call remote APIs safely without custom code. Settings.json configures PostgreSQL connection parameters. Within the MCP server's configuration block, you register the SQL server by specifying the command and arguments. For a Postgres server, you write command equals npx and pass the Postgres MCP package as an argument, along with your connection URI. Once registered, the client starts the MCP server process in the background. The server queries the database system catalog, compiling a list of all tables, columns, and indexes. It exposes the schema information to the agent as read-only resources, allowing the model to write accurate SQL queries. Database credentials whitelists protect production systems. When connecting the Postgres MCP server to a production database, you should never use superuser or write access credentials. If the agent has write access, a hallucinated or incorrect SQL command could execute drop table commands accidentally during debugging runs, destroying your tables. By creating a database user that only has select privileges and passing those read-only credentials in the connection URI, you prevent any data modification, ensuring that the agent can read schemas and query data safely without risking data corruption. JSON RPC schemas structure resource list requests. When the client communicates with the server, they exchange structured JSON payloads. The request payload contains 3 fields: genre, method, and params. For example, to list available resources, the client sends a request with method equals resources/list and an empty params object. The server reads this request, queries its local files or database schemas, and returns a response payload containing the resource list. If the client wants to read a specific resource such as a database schema, it sends a resources/read request, specifying the target resource URI in the parameters. The server reads the URI, retrieves the content, and returns the data block in the response payload. Local STIO subprocesses manage low-latency transports. The STIO transport is the default for local MCP servers. When using STIO, the client launches the server as a subprocess. The client writes JSON RPC request payloads directly to the server's standard input, and the server writes response payloads back to the client's standard output. Every request or response is written as a single line, terminated by a new line character. This DIO transport is fast and secure, as it requires no network ports or external firewalls. Server-sent events endpoints connect remote cloud services. In an SSE configuration, the MCP server runs as a remote web service. The client opens a GET request to the server's SSE endpoint, establishing a persistent unidirectional event stream. The server uses this stream to push notifications and updates to the client. When the client wants to send a request, it makes a standard HTTP post request to the server's message endpoint. This decoupled SSE transport allows you to connect local agents to cloud database schemas safely, routing requests securely through standard HTTP endpoints. Least privilege scopes secure OAuth integrations. When you authenticate an MCP server with an external API, the authorization flow displays the requested scopes in the browser. You should follow the principle of least privilege, granting only the minimum scopes required for the agent to complete its tasks. For example, if the agent only needs to read JIRA ticket summaries to debug an issue, you grant access to ticket-read scopes, preventing the agent from modifying tickets or accessing sensitive user data. The Claude Code client stores the OAuth tokens locally in your home settings under .claude/OAuth. If the token expires during a session, the MCP client automatically sends a refresh token request to the auth provider in the background, obtaining a fresh access token without interrupting your active development run. Database catalog schemas expose foreign key definitions. By configuring these local and remote MCP integrations, you transform the agent from an isolated text generator into an integrated automation engine, capable of querying databases, fetching tickets, and interacting with remote cloud systems securely. In our next section, we explore how to orchestrate multiple subagents to solve complex, multi-file software engineering tasks. We will analyze how JSON RPC schemas define parameters, trace standard input and output streams, and evaluate how the client manages access token overrides dynamically. The registry engine runs periodic diagnostics. When the client boots, it loads server parameters from settings.json. It verifies connection strings, checking if remote servers are online. If a server disconnects, the client flags the error, reporting it to Stout. It attempts to restart the server, restoring access dynamically without manual restarts, keeping your system operational. PostgreSQL system catalogs generate database metadata. When you register the Postgres MCP server in your settings.json file, the server process connects to your target database. It runs database query operations against the system catalog schemas such as information_schema.tables and information_schema.columns, retrieving metadata for all tables, columns, indexes, and foreign key relationships. The server compiles this metadata into a structured catalog, exposing it to the MCP client as read-only resources. When the agent wants to write a SQL query, it sends a resources/read request, retrieving the catalog. The model reads the table schemas, ensuring that it writes valid SQL queries, uses correct column names, and respects foreign key constraints, preventing syntax errors. TypeScript SDK classes compile custom server builds. If you want to connect Claude Code to a proprietary internal tool such as an in-house asset manager or a custom deployment API, you can build a custom MCP server. The TS SDK provides standard base classes for the MCP server process, allowing you to register custom tools and resources with a few lines of code. The server processes client requests, executes your local JavaScript functions, and returns JSON RPC responses, letting the agent interact with your internal services seamlessly. In-memory resource caches reduce HTTP request overhead. When the client retrieves resource data from an MCP server such as a large schema listing or a list of backlog tickets, it stores the data in a local short-term cache. If the agent requires the same resource information in a subsequent tool call, the client reads the data directly from this cache instead of making a network request to the server. This caching mechanism reduces communication latency and API overhead, keeping your automation runs fast and reliable, ensuring that the model always accesses the latest system schemas efficiently. Docker container virtualization isolates local MCP processes. When connecting the client to third-party or community-built MCP servers, you must prevent the server process from accessing unauthorized local files or communicating with external networks. You can secure these connection points by running each local MCP server inside an isolated Docker container, restricting the process's access permissions. The container mounts only the specific directories containing database files or source code, blocking the server from reading folders outside the container. You configure the Docker firewall rules to restrict outbound TCP sockets, ensuring that the server can only communicate with the local Claude client. This containerized isolation secures your workstation, preventing security violations and data exfiltration. JSON RPC exception mappings capture server crash logs. If an MCP server tool execution fails due to a network timeout or a syntax exception, the server must return a structured error payload. The payload contains error fields, code, message, and data. The client catches this error payload, wrapping the message details in a tool failure response. The agent reads the error, logs the details, and attempts to resolve the failure, ensuring the interactive session remains active even if a back-end server crashes. Process registry services restart disconnected servers automatically. When you register several MCP servers such as one for PostgreSQL, one for Jira, and one for GitHub, the client initializes a server registry. During the session, the registry monitors the health of all active server processes, tracking standard error streams and process status. If one of the servers terminates unexpectedly, the registry attempts to restart the process, restoring connection paths dynamically, keeping your automated tools active without manual shell restarts. On a busy construction site, a senior project manager does not dig the foundation, lay the brickwork, and paint the walls themselves. They hire specialized subcontractors, define targets, and coordinate the integration of their work. Subagent orchestration mirrors this workflow in the terminal. When you run a complex development task such as implementing a new feature across front-end and back-end directories, the parent agent does not edit every file in a single chat session. If it did, the conversation history would grow rapidly, pushing the session to the dumb zone. Instead, the parent agent acts as an orchestrator, spawning specialized child subagents to execute focused subtasks in parallel. By delegating tasks to subagents, you keep the parent session's context window clean and compact, preserving its position in the smart zone. /agents thread views display CPU statistics. When you run a task that requires parallel execution, the parent session spawns multiple subagents in the background. To monitor and coordinate these subprocesses, you use the /agents command. The /agents command provides an interactive manager, displaying an active thread list in the terminal. The thread list shows all running subagents, their parent sessions, execution statuses, and active CPU usage. If a subagent gets stuck in an infinite tool loop or consumes too many resources, you can select it from the thread list and terminate it, keeping your system responsive. Git Worktree add creates temporary workspace checkouts. To prevent file conflicts when multiple subagents edit the codebase in parallel, the framework uses Git Worktrees. If two subagents edit the same file in the same directory, they can overwrite each other's changes, leading to code corruption. To isolate their work, you configure an isolated worktree for each subagent by running the Git Worktree add command. A Git Worktree allows you to check out a separate branch into a different directory while sharing the main Git repository database. The subagent runs inside this temporary worktree, editing files, running tests, and committing changes in isolation. Once the subagent completes its task, the parent agent merges the worktree branch back into the main branch, avoiding file conflicts and workspace locking. AST-grep patterns parse structural syntax trees. When a subagent starts a task, it must identify which files are relevant to its instructions. Reading every file in a large repository is slow and wastes tokens. To filter the target files, the subagent runs AST-grep queries. AST-grep is a tool that parses code into an abstract syntax tree, allowing you to search for code blocks based on syntax patterns rather than plain text. For example, you can write an AST-grep query to locate all express route definitions that lack authentication middleware. The subagent reads the query results, compiling a list of target files, ensuring that it only opens files that require modifications. .agents/locks directories manage file system race conditions. When subagents run in parallel, they must write changes without race conditions. The framework coordinates this using lock files stored in .agents/locks. When a subagent starts modifying a file, it creates a temporary lock file. The lock file contains the subagent's ID and a timestamp. If another subagent tries to write to the locked file, the framework blocks the write tool execution and instructs the subagent to wait. Once the active subagent completes its edit and deletes the lock file, the waiting subagent acquires the lock and writes its changes. This lock mechanism prevents overwrites and ensures data integrity. Settings, profiles, customize subagent tool options. To optimize task execution, you can define different personas for your subagents in your settings.json file. The profiles define the model, system instructions, and tool restrictions for each subagent. For example, you can define a test engineer profile that only has access to test running tools, a debugger profile that has access to file reading and editing tools, and a secure reviewer profile that runs security scanning scripts. When the parent agent delegates a task, it selects the appropriate profile, ensuring that the child subagent operates with the correct tools and instructions. Context window isolation limits token consumption. By orchestrating these parallel subagents, worktree isolation directories, and AST-grep queries, you construct a scalable development pipeline capable of executing complex refactoring runs safely and efficiently. In our next section, we explore how to optimize your production performance and manage API costs using advanced settings. We will trace the detailed process coordination pipelines, examine file system synchronization locks, and evaluate how the delegation engine manages token isolation boundaries across multiple subagent execution threads. The process manager registers subagents dynamically. When a task starts, it creates a clean worktree directory. It copies dependencies, establishing a secure workspace. The manager routes task parameters to the subagent, initializing AST-grep filter rules. Once the child process completes its modifications, the parent session runs verification checks, merging the branches securely, maintaining code quality across your development branches. Asynchronous coordination loops monitor child tasks. When the parent agent delegates tasks to multiple parallel subagents, it must coordinate their progress and merge their changes without conflicts. The parent session manages this using an asynchronous synchronization loop. The loop runs in the background, monitoring the status of all active subagents, checking if any thread has completed its task or encountered errors. If a subagent completes its task, the loop validates its modifications, checking if the code compiles and passes tests. Once all validations pass, the loop merges the changes into the main development branch. If a subagent encounters a compiler error, the loop intercepts the failure, routing the logs back to the subagent's input channel, instructing it to resolve the error. This automated synchronization ensures that the codebase remains stable throughout the parallel run. Concurrency limits in settings prevent system CPU exhaustion. In large development containers, running too many parallel subagent processes can saturate the host system's CPU and trigger memory exhaustion. To prevent resource degradation, you can limit the maximum number of concurrent subagents in your settings.json file. For example, you set the maximum concurrency limit to 4. If the parent agent spawns 5 tasks, the process manager queues the 5th task, executing it only when one of the active subagents completes its run. This thread pooling keeps your workstation responsive, ensuring that automated refactoring tasks run smoothly without lagging your shell. Dependency maps resolve subagent execution order. If a subagent modifies a utility function that is relied upon by another subagent's target files, the parent agent must coordinate the order of execution to prevent compiler errors. The synchronization loop detects these code dependencies, parsing file references in the abstract syntax tree. It halts execution of the dependent subagent, waiting until the parent utility modification is completed and merged. Once the dependency is resolved, the loop releases the lock, allowing the subagent to run, preventing build failures and maintaining system consistency. Standard error redirection maps child streams to logs. When subagents run, their standard output and error streams are redirected to separate log files stored inside the .agent/logs folder. If a subagent fails or hangs, you can inspect these logs to troubleshoot the issue, reviewing the exact prompts, tool calls, and shell outputs of the child process. This transparent logging allows developers to debug parallel agent operations easily, keeping the system stable under all execution scenarios. Managing a metered utility pipeline requires strict controls: flow meters to track consumption, volume limits on each sector, and emergency shutoff valves to prevent runaway leaks. In automated terminal environments, cost telemetry and token budgets serve the same purpose. When running Claude Code in production or CI/CD environments, the agent executes tasks without human supervision. If the agent gets stuck in a recursive bug-fixing loop, it can consume millions of API tokens in a few minutes, resulting in high costs. The CLI framework provides a suite of advanced configuration settings, including non-interactive mode flags, budget limits, pager overrides, and automated context optimization routines that allow you to control consumption and optimize performance. Claude_non_interactive flags disable permission prompts in CI/CD. When integrating Claude Code with automated scripts or CI/CD pipelines, the agent cannot prompt you for permissions, as there is no human operator at the keyboard. To run the CLI in headless environments, you set the environment variable Claude_non_interactive equals true. When this flag is enabled, the CLI framework modifies its execution rules. It automatically approves all tool uses such as file reads, writes, and command executions without prompting the user. Additionally, the system disables all interactive prompts, redirects error logs to standard error, and returns the agent's final status as a shell exit code, allowing you to run automated refactoring pipelines inside containers. Session token budgets prevent API costs runaway. The budget setting defines the maximum number of input and output tokens the agent can consume during a single session. For example, you can set the budget limit to 100,000 tokens. If the agent's cumulative token usage exceeds this limit, the CLI framework automatically terminates the session, prints a budget exceeded warning in the terminal, and exits with a non-zero code. This hard limit prevents runaway loops from draining your API credits when running complex refactoring tasks overnight. Pager equals cat variable skip terminal viewport pauses. When Claude Code executes a command that prints long output such as a git log or a large directory listing, the shell can default to using an interactive pager utility, like less. An interactive pager pauses the terminal output, waiting for the user to press keys to scroll down. In headless automation scripts, this pause causes the execution to hang indefinitely. To prevent this, you should set the environment variable pager equals cat in your execution environment. The cat command prints the entire output stream immediately without pausing, ensuring that your automation scripts run to completion without manual intervention. Reinforcement learning feedback logs update active prompt templates. Named after the recursive feedback patterns of reinforcement learning, the Ralph loop is an automated context optimization routine. When the agent completes a task, the framework does not just end the session. It enters a local feedback loop, analyzing the execution logs, evaluating the token costs, and generating a brief performance report. If the report shows that the agent spent too many tokens on redundant tool calls, the Ralph loop rewrites the prompt templates, injecting context compression rules to optimize subsequent runs. This continuous context engineering ensures that the agent's prompts remain compact and cost-efficient over time. /usage dashboards monitor financial metrics in TUI. The /usage command displays your financial metrics in real time, detailing input tokens, output tokens, thinking tokens, and caching discounts for the active session. This dashboard helps you monitor your current spend and identify which subagents are consuming the most resources. The /usage credits command allows you to configure your payment settings and purchase extra API credits, ensuring that your automated pipelines never run out of budget during critical deployment runs. Headless automation scripts pipeline tasks non-interactively. By configuring these non-interactive modes, token budgets, and context optimization routines, you build a cost-efficient automation pipeline, capable of executing large-scale refactoring runs safely and predictably. In our next section, We explore how to bundle these configurations and scripts into modular, reusable packages using the plugins architecture. We will review how to configure usage budgets dynamically, trace cost analytics logs, and evaluate how the Ralph loop compresses system prompts to maximize caching and minimize execution overhead. The budget manager audits token transactions dynamically. When a session starts, it registers budget metrics from settings.json. It monitors token usage per command, updating the active count. If the session exceeds limits, the manager halts execution, printing a warning log. This proactive tracking prevents runaway sessions, protecting your development credits across all execution pipelines. /batch command queues process monorepo directories sequentially. When you need to run automated tasks across multiple repositories or packages in a monorepo, you use the /batch command. The /batch command accepts an instruction string and a list of directories. When executed, the CLI framework initializes a batch queue, processing the directories in sequence. For each directory, the framework sets up a temporary Git branch, runs the agent instructions, executes build validations, commits the changes, and moves to the next folder. If a folder fails a validation check, the framework logs the error, skips the directory, and continues processing the queue, ensuring that the entire batch runs to completion without manual intervention. IP whitelisting properties block external socket connections. When running Claude Code inside automated build nodes, you should restrict network access to prevent the agent from communicating with untrusted external servers. Within your setting.json file, you can define an allowed IPs property, listing your company's internal server subnets. The CLI security engine monitors all network socket connections initiated by the agent or custom MCP servers. If the agent attempts to fetch resources from an IP address that is not in the allowed subnet, the security engine blocks the connection, printing a network security violation warning in the build logs. This IP restriction secures your automated build environments, protecting your proprietary code from unauthorized exfiltration. Dynamic dependency caches save monorepo scanning tokens. When you execute the /batch command across a monorepo, the CLI caches the package dependency trees and file indexes of all modules in high-speed RAM. When the agent transitions from the first package folder to the next, it reads the shared dependency indexes from this local cache instead of performing a fresh repository scan. This optimization reduces the initialization overhead of subsequent batch runs, saving hundreds of thousands of input tokens and reducing execution times, ensuring your automated build pipelines run with maximum efficiency. Cost thresholds in settings manage API token expenses. When you plan repository-wide refactoring runs, you must estimate the token cost of each operation. The CLI framework charges different rates based on the model tier you use. For example, Sonnet input tokens cost $3 per million, while Thinking tokens cost $15 per million. To prevent runaway sessions from draining your budget, you configure usage limits in your settings, specifying a maximum cost threshold per session, such as $10. The billing manager tracks active token transactions, computing costs in real time. If the cumulative cost of the session reaches the threshold, the manager blocks further API requests, prompting the developer for approval before continuing, keeping your API spend within budget. Exponential backoff handlers wait out rate limit errors. When executing batch refactoring commands across dozens of repositories, your API requests can hit Anthropic's rate limits, triggering rate limit exception errors. To prevent build failures, the CLI client supports automated backoff and retry routines. If the API returns a rate limit warning, the client pauses the execution, waiting for the rate limit reset window to clear. It then retries the request automatically, ensuring that your automated build pipelines complete their runs without manual interventions, optimizing workflow reliability. Suppose you manage an industrial assembly line manufacturing automobiles. To switch production from sedans to pickup trucks, you do not rebuild the factory. You mount specialized tool attachments onto the robotic arms, update the software settings, and resume production. Plugins are those specialized tool attachments. While skills and custom/commands allow you to extend the agent's capabilities individually, plugins provide an enterprise-grade packaging system that bundles commands, skills, hooks, and configuration overrides into a single, modular package. By packaging your automated workflows into plugins, you can share them across your engineering team, version control them, and hot reload them dynamically, ensuring that your automated development environment remains unified and maintainable. Plugin.json manifest keys define command templates. A plugin is structured as a single directory. The directory must contain a subfolder named .claude plugin. Inside this subfolder, you create the plugin configuration entry point, a manifest file named plugin.json. The plugin.json file must follow a strict JSON schema. It contains metadata fields, name, version, author, and description. Additionally, the manifest defines the commands and skills that the plugin packages. For example, your manifest can declare a commands block mapping custom/command names to their markdown templates, and a skills block listing the paths to the skill.md files that should be loaded. Validation checks prevent plugin registry crashes. When Claude Code launches, the plugin registry service scans your project files and home directories, searching for .claude plugin folders. It validates the plugin.json manifests. If a manifest is missing required keys or points to invalid file paths, the validation engine prints a warning to standard error and disables the plugin, preventing registry crashes. If the manifest is valid, the registry service registers the custom/commands and skills, merging the plugin settings with your active session preferences automatically. /reload plugins sweeps rebuild command registries. When developing custom plugins, you often make changes to the plugin.json manifest, command templates, or hook scripts. If you had to close the CLI and launch a new session every time you modified a plugin file, you would invalidate the prompt cache, incurring high token costs and slowing down your feedback loop. To resolve this, you use the /reload plugins command. The /reload plugins command runs a hot reload sweep, rescanning your plugin directories, reevaluating the plugin.json manifests, and rebuilding the command and skill registries without restarting the active CLI session. This hot reload preserves your conversation history and keeps the prompt cache warm, allowing you to develop and debug custom plugins quickly and cost-effectively. Dependency audits check binary paths on boot. By packaging your automated workflows, custom hooks, and specialized skills into version-controlled plugins, you establish a modular extension architecture, allowing you to distribute custom developer tools across your entire engineering organization. In our next section, we explore how to automate teammate onboarding and monitor resource consumption in large-scale environments. We will trace the detailed plugin installation life cycles, inspect how validation errors are logged to standard error, and evaluate how the plugin registry service resolves name collisions dynamically. The registry runs validation tests. When the CLI loads, it parses the plugin.json directory list. It scans manifest parameters, checking for format compliance. If a manifest contains syntax violations, the registry logs the error, skips the module, and loads valid plugins, ensuring that your custom commands remain active and functional. Plugin hooks package pre-commit checks inside modules. Within the .claude plugin directory structure, you can add a hooks folder containing JavaScript execution files named precommit.js or postdeploy.js. When you register the plugin in your settings, the framework's hook manager automatically imports these files, registering them in the active session's hook execution queue. When the agent triggers a file edit or run a build command, the manager executes these plugin-defined hook scripts, running automated security scans and deployment audits. This packaging allows you to distribute secure hook guidelines to your entire team with a single directory clone, avoiding manual hook script copy-pasting, keeping your security gates standardized. Shared manifests cache plugins across monorepo directories. When you run multiple development sessions across different directories in a monorepo, the CLI framework caches the parsed plugin manifests and command templates in a shared system memory. When you switch directory paths and boot the CLI, the registry service reads the cached plugins, reducing launch latency to less than 100 milliseconds. This fast startup ensures that your terminal sessions remain interactive, preventing context compilation delays and making custom plugins feel like native system utilities. DevOps automation directories install manifests step by step. To build a custom plugin named DevOps Automation, you navigate to your home directory or project directory, create the DevOps Automation folder, and add a .claude plugin subdirectory inside it. Within this subdirectory, you create the plugin.json manifest file. You write the JSON object, defining properties name, DevOps Automation, version 1.0.0, author, DevOps team, description, automated deployments and health checks, and declare commands for deploy, rollback, and status. Next, you create a commands folder inside the plugin directory, adding deploy.md, rollback.md, and status.md templates. You also add a scripts folder containing the actual deployment shell scripts and configure a pre-tool use hook inside a hooks folder. You save these files and commit the directory to your project's version control. Once your team members pull the repository, Claude Code automatically registers the plugin, loading the commands and executing the deployment scripts in the terminal. Name collision handling favors high-priority plugins. If two plugins declare a / command with the same name such as /deploy, the registry service flags the collision. It resolves the conflict using a priority order based on the loading sequence defined in settings.json. Loading the command from the plugin with the highest priority and skipping the duplicate, ensuring that your CLI remains predictable and preventing runtime routing conflicts. Plugin scope settings override global preferences. Within your plugin.json manifest, you can define a settings block, specifying default token budgets, model priorities, or telemetry options for the plugin. When you trigger a command declared by the plugin, the framework automatically merges these settings overrides, ensuring the deployment subagents run with the correct budget limits and model configurations without changing your project's global preferences, keeping your automation settings localized and clean. Teammate onboarding in automated environments often suffers from configuration drift and manual setup errors. Rather than maintaining static documentation, modern teams automate setup using specialized onboarding commands. The /team onboarding command runs a system configuration wizard, checking the developer's local shell settings, verifying node and Git paths, installing missing packages, and pulling your team's centralized settings files from a remote repository automatically. Instead of writing and maintaining a static wiki document which quickly becomes outdated, you run Claude P/team onboarding. The command configures settings.json file path properties, registers custom plugins, and creates local directory rules, ensuring that every developer on your team works in the exact same environment. Observability metrics integrate token usage telemetry. When multiple developers run autonomous agents, the aggregate API costs can scale quickly. To monitor these costs, you integrate token usage telemetry with your company's financial monitoring platforms. You can export active session logs using the /export command or write a script that monitors your API usage. The CLI framework includes an automated session logging policy, writing every user prompt, tool call execution, and token cost metric to a local JSON file in your home settings under .claude/logs. Claude_telemetry_log_dir variables export audit records. In large companies, developers configure this variable to point to a network drive or a secure cloud bucket. When the CLI executes, it writes the session logs to this shared folder in real time. Observability platforms receive these session audits securely, mapping every tool call execution to specific developers, allowing engineering managers to monitor total token usage, evaluate caching efficiency, and audit security compliance across the entire organization. Distinguished AI Systems Engineer training wraps up. By finishing this lesson, you have gained a deep, staff engineer level understanding of how terminal-based AI agents operate and scale. You have learned how command routers map /commands, how Claude.md files leverage prompt caching, how Git index checkpoints enable safe rewinds, how hooks intercept tool calls, how MCP servers communicate via JSON RPC, how subagents isolate context windows, how planning mode builds reasoning trees, and how plugins bundle automated workflows. You are now equipped with the context engineering mindset and systems thinking needed to build, scale, and maintain highly optimized AI developer pipelines. Keep learning, keep building, and let the code run. The telemetry service validates workspace layouts. When a user runs onboarding commands, it configures remote URLs. It verifies connection pathways, checking if credentials match. If settings are updated, the service runs system checks, updating the local configuration, ensuring team alignment. Log scrubbing filters redact private passwords. If your organization operates under strict privacy guidelines, you must ensure that sensitive code-based data such as passwords, private tokens, or proprietary algorithms is never written to the centralized logs. Within your settings, you can enable a log scrubbing filter, checking the console outputs before they are written to disk. The filter parses the log streams, replacing any key value pairs or text that match pattern definitions with secure redaction blocks. This scrubbing secures your development metrics, allowing you to audit token usage safely without risking information exposure. Datadog and Prometheus dashboards monitor token spend. By feeding the compiled session logs into a centralized dashboard, your engineering leadership can monitor active spend in real time, The dashboard renders line charts mapping token consumption to specific repositories, showing which code bases consume the most resources. It calculates your average cache hit rate per team, displaying alerts if a repository's cache hit rate drops below 70%. This automated alerting prompts teams to lock down their rules and optimize their files, maintaining cost efficiency across your entire developer ecosystem, ensuring your AI automation remains sustainable and scalable. Fluent Bit logging daemons upload telemetry payloads. To integrate your terminal logs with a centralized observability dashboard, you begin by configuring the Claude_telemetry_log_dir environment variable to point to a secure directory on your local server. You set up a background logging daemon such as FluentBit or Logstash to watch this directory, scanning the JSON lines files for modifications in real time. The daemon parses each log transaction, extracting fields like session ID, developer username, API tokens consumed, and cache hit metrics. It packages this data into standard payloads, transmitting them securely to your centralized Datadog or Elasticsearch endpoints via secure HTTP POST requests. Once configured, you open your observability dashboard, configure the dashboard widgets, and monitor your organization's aggregate API spend, ensuring full visibility into your AI developer operations automatically. Automated auditing scripts scan telemetry logs. When developers run autonomous agent tasks, the logging engine records every tool execution and shell command run during the session. The security officer can write automated scripts that scan the centralized telemetry logs, checking if any developer triggered forbidden tools or executed dangerous scripts in production repositories. If a security violation is detected, the script logs the event, records the developer's username, and sends an automated alert to the security team, helping you maintain audit compliance and prevent data exfiltration. By exploring every feature, configuration, and integration of Claude Code from /commands and project memory to get checkpoints, hooks, MCP servers, subagents, and plugins, you have developed a staff engineer-level expertise in AI terminal automation. By applying the design principles, security gates, and cost management rules documented in this course, you are ready to construct, scale, and maintain advanced AI developer pipelines that drive productivity while protecting your code and keeping costs low. Thank you for listening. Keep programming and let the code run.